So our last video for this unit is looking at electrolysis. Now this is another application of these redox reactions we're looking at. And it's basically the opposite of a galvanic cell. So instead of using a redox reaction to make electricity, we use electricity to drive a redox reaction in the opposite way to the way they want to go. Okay? It's useful because we can use it to get pure elements out of compounds. We can use it to plate metals. It's also what happens essentially when you plug, say, your computer into the power supply and you're recharging your battery or your cell. So electroplating is a really useful one for cutlery, for jewellery, for cans, all of that kind of thing. What we essentially do is we get one electrode, which we make out of the metal we want to plate with. The other electrode we make in the object we want to plate with. And this time, for all electrolysis, we stick it all in the one beaker. Okay, we don't need to separate them because they're not going to react on their own. We've got to put the power supply through to do that. And then we put them all in a soluble salt of the metal we want to plate them with. Okay, so in this picture here, for instance, we want to plate a spoon with silver. What we're doing is we use this source, this power pack, could be a plug, could be a power pack, to force electrons the way we want to go. Now electrons, remember, are negatively charged, so they're going to be attracted to the positive of the power pack and repelled or pushed away from the negative. So we push electrons down onto the fork. This becomes negatively charged, so it attracts this positively charged ions. So they go onto there and they turn into silver atoms. Here we're pulling electrons away, and what we're doing is we pull them away from the silver atoms, so the silver atom turns into silver ions. Same principle here. We're just using copper instead of silver, okay, to make a copper-plated key. The way it works, the anode, which remember the anode is always the site of oxidation, okay? We are pulling electrons away, okay, and we are oxidizing it, turning those metal atoms into metal ions, which go into solution. At the cathode, we push electrons on, becomes negatively charged, attracts the positively charged ions, and they will make the silver atom. We've still got two half equations, one for each electrode. We can't make an overall equation though, because it's going to exactly cancel out. So you'd never be asked for the overall equation in electroplating. Okay. We can also do electrolysis of molten substances. So we get something where we've got ions and we heat it up a lot, so we melt it, okay? And then we can split it up. So, same basic principle. The positive of the battery is going to attract electrons, okay? And it's where oxidation is going to occur, okay? So in this instance, these negative electrons are going to be attracted to the positive anode, and their electrons are going to be taken away from them. And the negative will attract a positively charged ion and it will give it electrons. Here's what it actually, a better diagram of what it looks like. This is called a down cell. Same reaction, okay, still sodium and chlorine, chloride ions. We're making sodium metal and chloride, okay. But in the actual industry, what we've got is a hood here, which collects the chlorine gas and takes it away. And we've got cathodes, which are able to have that metal being made, and that will float away, and we want to get them separate from one another, because if they touch each other they're going to react pretty violently, and that's not going to be good for us, okay? But it's basically the same thing, and we can keep on adding the sodium chloride in there, okay? This is a commercial way of making sodium metal from sodium chloride, and it gives us chlorine gas as well, which can be useful for things like swimming pools, where we really need the chlorine in order to act as a way of killing the bacteria. Okay? We've got to keep those two products away, or they're going to immediately react to make the sodium chloride again, because that's the way it wants to go. Remember, in electrolysis, we're driving it the opposite direction.